Assalamualaikum and hi everyone. Welcome to our video about photocatalytic degradation of organic pollutants by titanium dioxide. Without further ado, let's continue.
Photocatalytic degradation refers to a process where a catalyst, typically a semiconductor material like titanium dioxide, is activated by light to degrade organic pollutants into harmless byproducts through oxidation reactions. It started to be used in the late 20th century. Researchers began to explore the use of titanium dioxide photocatalysis for the degradation of various organic pollutants such as dyes and pesticides in water and wastewater. This technology offered a sustainable approach to address environmental pollution issues by utilizing the power of sunlight or light to activate the photocatalyst and break down harmful organic compounds into non-toxic byproducts. Next, the history. Discovered by chance by Akira Fujishima, a graduate student working under the guidance of Associate Professor Kenichi Honda. Announced in 1972 in the journal Nature, and is now called the Honda-Fujishima effect after its discovery phenomenon of photoelectrochemical water splitting on a titanium dioxide electrode, realized that the same principle could be applied to degrade organic compounds in water and air. Next, working principle based on applied physical chemistry. First, band gap excitation. When the photocatalyst is exposed to light, photons with energy equal to or greater than the band gap of the semiconductor material are absorbed. This absorption leads to the generation of electron-hole pairs in the semiconductor. Second, redox reaction. The generated electron-hole pairs participate in redox reactions with adsorb organic pollutants on the surface of the photocatalyst. The electrons can reduce oxygen molecules to form superoxide radicals or hydroxyl radicals, while the holes can oxidize water molecules to form hydroxyl radicals.
My name is Farah and I'm going to present the methodology lab by synthesis of titanium dioxide nanoparticles. This method is based on a study by Koliv and Raja Karuna where the ilmenite is crushed, ground, chemically treated with aqua regia to extract titanium dioxide, which is then neutralized, heated and calcined to produce titanium dioxide particles. The methodology involves crushing, sieving and the ilmenite to obtain the particles, followed by leaching with aqua regia to separate titanium dioxide and ferric chloride. After filtering and neutralizing with ammonia, heating at 90 degrees Celsius for 30 minutes precedes drying at 105 degrees Celsius for 2 hours, calcination at 550 degrees Celsius, which produces titanium dioxide nanoparticles. Is the method for photocatalytic degradation using titanium dioxide of organic material in laboratory. This method involves in preparing a stock solution for pollutants, setting up a photochemical reactor and immersing the solution with titanium dioxide photocatalyst under oxygen bubbling. Initial readings are taken in the dark before irradiating with a medium pressure mercury lamp. Samples are collected at intervals for analysis, including under sunlight exposure in subsequent trials. As you can see in the picture here, this image illustrates the equipment used in the method. Figure 1.1 shows various lamps including medium pressure mercury arcs used for irradiation in the reactor setup. Figure 1.6 shows a cylindrical vessels exposed to the sunlight, demonstrating the experimental setup for utilizing solar radiation in place of artificial lamps. This will enhance the versatility of the photocatalytic process. Furthermore, the diagram shows here a photochemical reaction vessel designed for studying the degradation of organic pollutants using titanium dioxide nanoparticles. This setup, equipped with a UV or visible light source, a quartz vessels, a cooling system, a magnetic stirrer, and oxygen supply, efficiently breaks down pollutants into less harmful substances. This demonstrates titanium dioxide's potential in environmental remediation. There are several methods for measuring photocatalytic degradation, but I choose these common three methods by examining BOD, COD, and using UVV spectrometry. BOD assesses oxygen consumption by microorganisms during organic pollutant oxidation, with lower values indicating successful degradation. COD measures oxygen requirement for chemical oxidation of pollutants to carbon dioxide and water, showing effective oxidation through decreased values. UVV spectroscopy monitors pollutants absorbance, where decreasing absorbance means degradation, providing insights into degradation efficiency and also kinetics.
Hello, my name is Lee Wen Yao and I will discuss about the result and discussion in this assignment. The pictures below shows the titanium dioxide nanoparticles synthesized by Mamadov and others in their investigation during 2017. In the SEN image, it is clearly seen that the nanoparticles produced were homogeneous and had diameters around 15 to 30 nanometers. Purity and crystalline properties of nanoparticles were investigated through XRD. All of the XRD lines indicate that the crystal is in rutile phase and its average size is 18 nanometer based on the 110 peak. This page shows the graph obtained from the titanium dioxide photocatalytic degradation investigated by Hake and others in 2012. Without a doubt, the efficiency for photocatalysis of organic pollutants was increased enormously with the addition of titanium dioxide that indicated by decrease in absorption intensity and depletion in total organic compound content as shown in the left graph. Other than that, the mineralization and decomposition rate can be fitted in exponential decay curve that suggests both reaction follows first order reaction and their rate were able to be calculated precisely. For the mechanism, titanium dioxide is a type of semiconductor, hence it does not have continuum electronic states like normal matter but contains void region that known as band gap. Band gap is located between the highest occupied molecular orbital, or known as the valence band, and also the lowest unoccupied molecular orbital, or commonly known as conduction band. When light is shined onto titanium dioxide, it will absorb photon energy and cause electrons to be excited and migrate from valence band to conduction band. As a result, a hole is generated at the location. Later, the electron-hole pair migrate to photocatalyst surface for the recombination process. During the process, the hole will oxidize water to hydroxyl radicals that will initiate a chain reaction, whereas electrons is donated to electron acceptor like oxygen and metal ions to form reduced form of ions. The combination of hydroxyl radicals and reduced ions are able to degrade organic compound through redox reaction. So, how do we able to improve efficiency of photocatalytic degradation? Well, there are 6 ways to do it. Firstly is to increase the light intensity. The greater the intensity of light, the higher the efficiency. Next is the temperature, where higher temperature will enhance recombination of charge carriers and the desorption process of the absorbed reactant species. Aside from that, the nature and concentration of substrate have impact on the efficiency. Molecules that has electron withdrawing group will more adhere onto surface of photocatalyst, while high concentration of substrate decrease the rate of degradation. After that is the pH value, where optimum pH of solution will have optimal efficiency due to the change of charge for photocatalyst surface. Later is the concentration of photocatalyst, where optimum catalyst concentration can avoid catalyst wastage and ensure total absorption of photons. Lastly is the nature of photocatalyst, where it depends on the size and surface morphology of the catalyst.
Countries like China, Japan, and United States that utilize photocatalytic degradation technology for various applications. First, air purification. NOx is oxidized and converted into nitrate ions. The nitrate ions are washed away when it rains. Second, self-cleaning. Reduce absorption of dust and other particles. The layer of water reduces absorption of dust and other particles through static electricity. Next, helps stop oily dirt from sticking. Activated oxygen decomposes dirt clinging on the surface and helps prevent it from sticking. And the last one is harnessing the power of the rain to wash surfaces. Rainwater gets in under dirt, lifting it off the surfaces and washing it away. So, what is the differences between this method and lab-based method? First one is resource availability. Lab-based method. Laboratories may have limited resources in terms of equipment and materials. Companies and countries have access to greater resources for research, development, and implementation of photocatalytic technologies. Second, parameter optimization. In the laboratory, researchers focus on optimizing parameters such as reaction time, pH, and temperature. Consider factors like reactor design, flow rates, and scalability to ensure consistent and effective degradation of pollutants in real world. The last one is experimental condition. Laboratory experiments allow for precise control over experimental conditions. Practical applications may involve adapting the method to real-world conditions.
Other than titanium dioxide, zinc oxide can also be used as a material for photocatalytic degradation of organic pollutants. However, there are several differences between the titanium dioxide and zinc oxide in the application of photocatalytic degradation. Titanium dioxide has more stable structure and are non-toxic compared to zinc oxide. Titanium dioxide also has higher efficiency in degrading organic pollutants than zinc oxide. This is due to the higher recombination rate and potential stability issue of the zinc oxide. In terms of cost, both materials are inexpensive and are widely used. For the mechanism of titanium dioxide and zinc oxide, both have similar mechanism involving light absorption, charge carrier separation, and redox reactions to degrade organic pollutants. For light absorption, both materials will absorb UV light, then excite the electron from the valence to the conduction band. The only difference is that the titanium dioxide has a slightly lower band gap compared to the zinc oxide, which affects the wavelength of light each material can absorb. Next, for charge carrier separation, the generated electron hole pairs for both titanium dioxide and zinc oxide are separated. It is crucial to reduce their recombination. Though, zinc oxide tends to have a higher combination rate, potentially reducing its photocatalytic efficiency. For degradation of pollutants, titanium dioxide and zinc oxide generated reactive oxygen species that are highly reactive and can oxidize organic pollutants. Another material that can be compared with titanium dioxide in terms of photocatalytic degradation is the cerium oxide. Cerium oxide is highly efficient, especially when oxygen vacancies are optimized. Cerium dioxide also can absorb UV light and near visible light, while titanium dioxide is only limited to UV light. In terms of stability, titanium dioxide exhibits superior chemical stability compared to cerium dioxide, and they are much less expensive to be used. Both titanium dioxide and cerium dioxide are efficient photocatalysts. They also exhibit similar mechanisms that influence their photocatalytic activity. Titanium dioxide and cerium dioxide generates an electron hole pairs upon light absorption. Cerium dioxide has oxygen vacancies that can trap electrons, reducing the recombination rate of electron hole pairs and potentially enhancing photocatalytic activity. The reactive oxygen species in titanium dioxide and cerium dioxide will oxidize and break down organic pollutants into less harmful compounds. Cerium dioxide have a unique feature in which it has the ability to store and release oxygen due to the reversible redox couple. This capacity enhances its ability to generate reactive oxygen species continuously. In summary, the use of titanium dioxide in the process of photocatalytic degradation of organic pollutants is extremely effective because of its strong operational principle and efficient degradation mechanism. Laboratory scale methodologies provide essential insights and optimization strategies, facilitating the transition from experimental setups to real-world environmental remediation technologies. Titanium dioxide is an exceptionally efficient photocatalyst for breaking down organic pollutants due to its distinctive characteristics and processes. Titanium dioxide's photocatalytic activity is mainly driven by its capacity to absorb UV light, leading to the production of electron hole pairs. Titanium dioxide has a band gap of around 3.2 eV, which allows it to effectively capture ultraviolet light. This absorption of UV lights leads to the creation of electron hole pairs, which in turn initiate redox processes in the surface of titanium dioxide and successfully degrade organic pollutants.